Good morning. I'm Erik Nordmark. I'm CTO at a company called ZEDEDA. I work on this project as part of the Linux LF Edge called Project Eve. I'm here to talk about what we have seen from customers deploying edge computing in various sort of industrial and similar environments and what it means from a security perspective in particular. So I don't know, how many of you guys have actually heard about Project Eve before? You can raise your hand, like 2 or something like that. So I'm not going to go into a lot of detail about what it is, but let me talk a little bit when we get to those slides. And if you have any questions, we might be able to take those, since it's a small group, take them during the session or afterwards. So, and there's a microphone up here for asking questions as well, so remote attendees can hear them. So the edge actually means different things to different people. So this is actually out of a white paper that LF Edge actually put together, talking about the ranges from it. If you're coming more from the telco service provider side of things, you're more sort of off towards that greenish side, right? The area that we look at is the smart device edge, sort of on-prem data centers, things that are a lot more distributed, but not going all the way down to the sensors, actuators, the actual constrained devices, but things that are actually programmable. But what are some of the challenges out of this distributed edge? Well, when you go and deploy things in factories, in retail locations, wind turbines, whatever, you don't necessarily have the same network security boundary that you have when you're running this in your own data center in the cloud. You don't necessarily have the same physical security boundary. In some cases you do, right? Climbing up into a wind turbine, there definitely are locks and cameras before you get there. But there's other cases, like in retail, where you might not have much of it at all. And the applications, particularly if the applications that have been developed to run in the cloud, most likely they actually assume that both of those things are in place. And concretely, there is security issues like, what happens if someone walks up with a USB stick, right? What can they actually do? Or plug in anything else into any open port on the actual device, right? And here, devices could be a ruggedized, very capable server with multiple GPUs, etc., right? It could be some IoT gateway, some smaller form factor thing, but they typically have a rich set of I/O connectivity. But the other thing that people can concretely do, if they have physical access, they can actually go in there and they can actually try to reflash the BIOS, right? It might depend on the BIOS settings, but you might be able to change some other firmware. You can definitely steal the whole device. You can steal or duplicate the disks. So this is things that you don't have to worry about in a data center or cloud deployment. And some of these concerns actually apply to the infrastructure layer, right? Can I actually clone this device? If I have a temperature sensor in this room or something that actually does analytics of the HVAC system in this building, can I clone that thing and have something else actually play a completely different story, right? So that whoever is receiving that data now at best gets confused, but might actually do the wrong thing. And of course steal the whole device, but if you're talking about applications, it might be more that there's something interesting in this data. If you're doing oil and gas exploration, the value of the data that you actually extract from your sensors is extremely high value, right? Your applications might be proprietary that you actually go deploy. So you can actually do those things as well. Or corrupt it, because you want to make people do something different. And you have to be concerned about connectivity. Well, connectivity is not a security issue, right? But as I will talk a bit more, sort of some of the ways you deal with these issues is actually depending upon having connectivity. And out at these locations, you might have intermittent connectivity because you want to operate things. You want that factory to continue working, that well site continue drilling, even if the internet connectivity goes down, because you don't want to stop the process. And there's some additional things that in a cloud deployment, there's somebody that owns and operates the cloud infrastructure, the switches, the routers, right? Azure, AWS, whatever, right? And you as a user, you come and you deploy your applications. Well, out at the edge, it's even more nebulous in terms of the different parties. You know, GE Medical deploys imaging devices in hospitals. They don't actually know what the hospital IT admin has set up in terms of network security, because that's a completely different organization. In fact, when I talked to them, they said, we don't even talk to those guys, because they sell things to the X-ray doctor. And then he hands them over to, you know, the IT department saying, hey, you guys go connect this thing, right? So there's a completely sort of different organizations with potentially different priorities in this picture that makes it slightly more complicated to say, well, do we know anything about the baseline where in the environments where these are deployed? And in general, we don't. There's other things you might be concerned about at scale. You know, sure, the thing you deploy can actually be subject to distributed denial of service attacks. That's something that you have to be concerned across the board, even if you're deploying things on the edge. But the thing in addition is actually outbound DDoS. So if some attacker actually manages to get things installed on these devices and there's, you know, 100,000 of them, well, what type of DDoS attacks can they launch from those sites with their aggregate bandwidth? So these are things that are, you know, somewhat unique for the distributed edge. So let's talk about two different use cases, sort of abstracted away a little bit. This first one is for oil and gas. So you have some ruggedized servers installed on trucks. These servers are actually drop shipped from the manufacturer, where they actually are installed with the software. And then these things actually get drop shipped out into various countries. These things, the trucks actually move around. So some cases they're actually at some base where they have network connectivity, might have wired stuff, Wi-Fi, whatever. In other cases, they're out in the field and maybe they have LTE, but in many cases, at best they have satellite, which they don't actually want to use to do lots of stuff. They don't want to do, you know, update the software over satellite because it's a bit expensive. And they can actually be out in these places where they effectively are disconnected from the internet for a week, right? Everything should continue working, and then they come back and the data actually gets uploaded, or the results of the analysis gets uploaded. In this case, there's actually a local operator there, but that's a local operator that's actually in charge of the operation, right, of what they're doing out in the field, not somebody who's an IT admin or some security admin or anything. It's someone that can go and reboot things, power things on and off, but that's sort of the extent of it, right? The applications contain intellectual property, right, that they don't want to share. The gathered data is also very sensitive. These applications, they must keep on running even if there's no internet connectivity, in particular if, you know, and they might actually end up restarting and rebooting things, power cycling things as they, while they're out in the field. So this thing needs to come back up and run things. And there's typically quite long deployment life cycle for these things. I mean, that's true for edge computing in general, that whereas in data centers cloud, you might replace the hardware 2 to 3 years. Here it might be more likely that it's 7 years. It might depend on the applications and when do they need more capacity out there. So you definitely need to push out not only software application updates, but most likely firmware updates during the life of these devices. But there is concern about, you know, how do we handle, you know, zero-day ACVs? How can we actually get patches out quickly? Sure, when it's out for a week and it's not connected, you're probably not going to deploy the patch. But you want to deploy it as soon as it actually comes back and connects up to the internet again. So scale in this case is, you know, thousands of locations, right, that you need to worry about. So that's one use case. The next one is actually a retail case that actually comes from car dealerships. So again, these servers are installed out at dealers. They're typically drop shipped out there. The dealer might be a sort of an owned dealer from the actual car manufacturer, but it might be a completely independent party as well, from sort of an ownership perspective. And here, you don't typically have much control of the enterprise network in which it's connected, right? The dealer has some network, some internet connectivity. You get an Ethernet port to plug in, and maybe you're told that, hey, go use this VLAN or whatever, and that's about it. There's no local operator here that sort of works for the entity that wants to control this, some central IT organization, whatever. But you might want to manage applications even if the enterprise network is down. So in one of these cases, they actually are deploying this with an LTE modem solely inside the server, solely as a fallback. So they can at least see that, hey, this thing is still alive and out there, and actually being able to troubleshoot some things, even if the dealer's network is actually not currently working. You can have application data that's very sensitive in this case. Part of that has to do with the relationship between this and software and firmware that actually goes into cars, right? Where there's actually an increasing set of compliance requirements around what the supply chain needs to be for the delivery of that software into the cars. But again, you need to keep things up and running. You don't want the dealer to sort of grind to a halt just because the internet connectivity drops for an hour and continue doing things. In this case, BIOS update seems to be something that they believe will actually happen. The other thing is that the storage capacity of these things might actually increase over time. The amount of software that goes into cars is actually increasing quite rapidly with all of the move towards electric vehicles, etc. So that you need to be able to go out there and have some field technician plug in more SSDs, NVMe drives, whatever. Scale of this could be tens of thousands of locations spread around. So these are actually real cases where we've been deploying Project Eve out in the field and sort of figured out over time, over a couple of years, what does it mean to do security in this. And in terms of security, what people traditionally do doesn't quite fit this. So back in the old times, people had these standalone devices, right? Embedded computers were not connected to the internet. Well, in that case, you didn't have to do anything because you built the thing, you put the software on there, and you said, yeah, I never have to touch this thing again, right? It will die, I will throw it away. But as soon as you connect something to the network, you have to be able to deliver some patches and a minimum security patches because you're going to find another heartbleed bug in the SSL stack somewhere, right? Something that you have to fix. So that's a given. So how do people actually do this today? Well, there's two ways. One is the data center, where you have your own mechanisms for doing this. They can basically reinstall the servers completely, right? You're running your applications as virtual machines or containers, but you have complete physical control of the environment, and you have very deep network security mechanisms in place. And as a user, you might not see those because it might be AWS and Azure that give you some knobs, but what they're actually running in the background, you may or may not be aware of. So that's one environment that exists, and a set of techniques for dealing with it. The other one that exists is clients, right? Whether it's a laptop, a smartphone, whatever. And in those things, there's some form of another of full disk encryption, right? Or partial disk encryption, which is actually tied to the user typing in their PIN, their fingerprint, their face recognition, whatever, to sort of unlock the device, and doing that on each boot. That's a technique that works quite well, right? But if you don't have a user in front of the screen because this is sitting in a wind turbine 100 miles away in the middle of West Texas, you don't want to have the user come over just because they need to put a fingerprint or a password in. So, and where can you actually store it? Well, yeah, you can store it on the drive, right? On the SSD. Well, what's the point of storing a password on the SSD if you're concerned that people might get physical access to this? Because now they have that password as well. So it's like you have no firm ground to stand on to actually do something like that. The other thing that people actually do is they employ a technique called secure boot, which is basically based on having a chain of signatures and everything throughout the boot chain, so that the BIOS actually trusts some bootloader based on some hashes, based on some signatures or whatever, which basically ensures that, and in the typical way this was initially done was Microsoft ensuring that, yeah, you could actually boot Windows, you might not be able to boot anything else because it had to be signed by Microsoft. It's a bit more flexible today, but fundamentally it's based on the signature of the entity producing this stuff being something that's approved by other parties of the boot chain, like in the BIOS, right? The set of trusted entities are in there. Well, the challenge with this at scale is dealing with, signing means I know who produced it. It doesn't mean it's bug-free, right? The Heartbleed bug example, well, that clearly was in lots of signed software, right? Because it was in the OpenSSL library that most of the planet actually uses. Was probably also in FIPS 130 and other forms of FIPS 140 and other forms of certified to be secure software. But it still had a bug. So how do you actually roll that stuff out? The signature just says no one else has modified this stuff. It was produced by somebody that picked that through the supply chain and distributed it, but it's still a bug that needs to be fixed. So how could you do this at scale? In theory, you can do this because you can go in and blacklist, hey, that particular thing with that particular SHA should not be trusted anymore. But I've seen nobody describing how do you actually do this stuff at scale to 10,000 devices when you need to go and update the BIOS to blacklist a particular SHA, right? It doesn't work. And you need to worry about, in addition to that sort of thing, what happens while things are actually shipped, right? Can someone actually revert back to the old signed version of the BIOS, right, that has some bugs, or the old signed version of the OS that has some bugs, because it was signed, right? It was signed 3 years ago. But you don't actually know, using this technique, is this actually a current thing? Another thing that's sort of starting to evolve more, particularly around smartphones and other devices, that people that operate the sort of backends, right, your bank, might build things so that you actually remotely attest. So that when you come in and want to run your banking app, it basically attests that the software that's running on your phone is actually the current one. And based on having various measurements, various chips, security chips that support this stuff. So now you can actually, the bank, before it allows you to transfer data, can actually check that, hey, this stuff is actually a valid, iOS, Android, it's my app, not somebody else's app that I'm talking to. In addition to the security measures of you actually logging in, two-factor or whatever, right? But actually validating the hardware and software to some degree. So that's very useful. But as I mentioned, these early ones, it's like, well, but you need to be able to do this stuff even if you don't have internet connectivity. The thing needs to come up and run this application to operate your wind farm, even if the internet connection is down. So how can you do that, go and attest to something? That doesn't quite work. So we started 5 years ago or something like that on what became Project Eve. And one of the things we started looking at from the beginning was sort of how do we figure out security? So to give some context, right? So Eve is this thing, stands for Edge Virtualization Engine. It runs on your edge devices out in the field. It is managed using an API. This part is all open source. The API is all open source. There's some open source controller that, for cuteness reasons, are called Adam, and something else called Eden to drive this stuff. There's also a commercial controller today from ZEDEDA, right? But anybody can go build the same thing. And it sort of leverages hardware security, trusted platform modules and things, runs different apps, decouples. This is the management, orchestration system. What the users do with their data from their oil exploration, whatever, that they do whatever they want with, right? Doesn't get involved in that part of things. So that's sort of the context of this. And then what did we do in terms of security? Well, the key thing was actually starting to think about security from day one. And saying that, well, this is a device. It doesn't need any usernames and passwords. Because there is that controller in the picture, right? When you go on through a user interface, you're not talking to the device, you're talking to a controller. That's where you do your usernames, passwords, two-factor, RBAC, whatever, right? But you actually keep the device simpler and actually uses public keys, certificates, whatever, as the way of actually identifying it. And then look at the whole life cycle of this device as well as applications out at the edge. From the sort of factory, what happens when you actually install the Eve runtime on this stuff? Can you actually get baselines about what is this piece of hardware? Can you actually save those things? And pre-installing sort of data sets, if you have lots of data volumes, you might not want to have those things be downloaded when it's out in the field on a slow connection. So you can do various things there. Look at how do you actually securely onboard this, either in the factory or out on location, so that it's actually part of and known to the controller. And then deliver patches, updates, whatever apps, right? And then decommission it if either it's sort of out of its service or for some reason you don't actually trust it anymore. You can actually go and decommission it. So this is, most of what this stuff is doing, it's taking a bunch of tools we already have. Trusted platform modules and similar things, right? Crypto-based identifiers, TLS, measured boot, remote attestation, disk encryption, distributed firewalls, a long list of things, right? Signatures, being able to deploy VNFs, right? Virtual firewalls, if you want additional network security, you can actually run it on the box itself to protect what's over there. Using hypervisors to do strong isolation. And then the other things that, as we worked with these use cases and these users, we realized that in the real world, well, where I come from, right? I've been active in the IETF for a long time, saying that, hey, I can do mutual TLS with client certificates. I control both ends. This is secure, right? I know about the security properties of this stuff. It's great. You go out in the real world and you find that, hey, these guys have the content inspecting proxies and they're run by the hospital admin, right? The people building the equipment can't actually control that stuff. They don't even interact with that person, right? Or that policy. So you have to be able to deal with that. Well, I'll talk a bit more about that. And then the other thing is this, okay, how can I actually do something sensible about handling firmware and software updates without actually exposing it to losing my application data out in the field to an attacker? So, I don't know if people are familiar with content inspecting proxies or enterprise proxies or TLS man in the middle, depending on your perspective. But you see this typically that when you start at a new company and you want to bring in your cell phone, they say, hey, please add this key to your keychain, right? Or the IT department gives you your corporate laptop, phone, whatever, and it has that stuff installed. There's actually another one, which I think is less common nowadays, which is, but you can set them up that way to just basically spoof certificates on the fly. So when you go and ask for the certificate for Windows update.microsoft.com, the proxy makes one up on the fly and assumes that you will actually trust it somehow. This is actually supported by most open source as well as commercial web proxies, right? I have no idea how common this is out in the real world. But this notion that, hey, at this company, you add this thing to sort of trust the firewall, you add this certificate to your keychain, that I have experienced myself. And by the way, they're different perspectives. Some people think these are bad, right? Because they're breaking end-to-end security with TLS, right? Other people say, well, no, but we need this stuff to be able to make sure we're not losing intellectual property or that we're getting viruses coming in. We need to be able to look at the content, right? So, you can have different perspectives on these things. But we felt that, well, for these types of applications, you don't want, particularly if that's a different organization in charge of that proxy, you don't want them to be able to control the valve in the power plant, right? They can look at the content, but they shouldn't be able to modify it. So we actually ended up with these three layers where, in this picture, we have some node running out at the edge. We have some proxy over here. We have the management and orchestration system over here. And we're running TLS. But TLS is basically being intercepted with this man in the middle over here. So the TLS layer is the base layer. But then if this thing is actually intercepting things, well, now you can actually configure it just like your phone, saying, hey, put this thing in your keychain. But there's another layer of signatures end-to-end, as well as selective encryption, object encryption on top of that. So it's something that I pushed back saying, this doesn't make any sense. Why do we have this thing in the middle? But real world says, well, you actually want to run in the real world, so let's make something that's a bit more complicated than I would have liked. But it actually is something that's important. Next thing is measured boot remote at station. How do you actually do this stuff? If you, because of this so measured boot and remote at station is something that is there in the standard from the Trusted Computing Group. It's not widely used. Some of the things that people are doing with this remote at the station to your bank type thing example, it's starting to use some of these pieces, right? But the key thing is that being able to detect, did somebody actually change the hardware, the firmware, the software? If no changes happen, then we can just go ahead and boot things, run in the applications. If something changes, we still want to be able to remotely manage this device to see that it exists. So you can actually see that it wasn't that the power supply died. It's something else that's going on. Maybe there's someone who didn't know what they're doing, and they just recabled the PCI cards inside the server, and that causes the hardware to measure differently. But if something changed, the device still boots. It connects to the controller. It says, here are my measurements. And you will not be able to access, the applications will not be able to boot because they cannot access their volumes anymore. Their data is still encrypted. And then you can actually detect and report this thing. The user or policy in the controller can then decide to approve this new firmware, software, whatever, hardware reconfiguration either ahead of time or when it actually shows up. So that's a sort of key requirement that a power outage while you're out in the field and the internet is down, the application better come up, right? Otherwise you have big operational problems, not security problems, but operational problems. I don't think I'll go into this detail. There's a URL at the bottom. I'll share these slides later, but it's leveraging the stuff that's there, but no one had put together a system like that before. So, but sort of Project Eve in summary, right? The key thing is that the device is always remotely manageable. And the policies are decided by the user/controller. You're keeping the security policies sort of out of the device, right? And doing this stuff remotely, but having it in a way that it could still function when it's remotely connected. And since I needed some colorful graphs, I had to show the apps being the tip of the iceberg, but there's lots of other things. I've mostly talked about security here. Some sort of takeaways here. If you care about the stuff out at the edge, where people potentially have physical access to your devices, you don't have the same level of network security, what should you ask of your hardware and firmware supplier? Well, one thing is hardware root of trust, right? Does this thing have a TPM? Does it have some other form of hardware root of trust? Like on ARM devices, you can do the same thing with trust zones and effectively firmware TPM. Also, do you care about hardware chassis intrusion? So there's one thing if someone just walks up and plugs in a USB stick or walks by and pulls out the NVMe drive. But another thing you can do is if you can open the chassis, you can actually put probes on the various buses inside the system. So with TPM chips, there's an interesting thing that you can put probes on the bus between the CPU and the TPM chip. This takes a bit longer, so the attacker has to spend some more time to go do that. But if you care about this stuff, you might want to have some chassis intrusion detection to just make it slightly easier or slightly more detectable to do this. Nothing is perfect, right? Hardware tamper-proof is a completely different field. We're just talking about software. And then there's other things about if you're going to have 100 identical devices, it's a lot more scalable if these measurements you get from them are identical. But identical is rather picky, right? If you actually measure the firmware version of your SSD controller, if that happens to become part of the measurement, well, maybe midstream they actually change this stuff. Or if the disks don't have identical size, identical in terms of the number of blocks, the partition tables will actually measure differently. Right? So really doing this stuff at scale where you say these things are identical, meaning that they measure identically, you actually have to pay close attention to the hardware as it's built, right, and as it evolves. Any application considerations? Well, the application needs to be secure, but in Eve we actually put something, a distributed firewall, right? Plus, as I mentioned, you can actually deploy other sort of VNFs, right, that do firewalls, SD-WAN, whatever, right? And what level of support you need there to sort of provide a sandbox at the edge for your application depends on your application. What assumptions does it have, right? Is it really built assuming that it has the security groups inside the cloud? Well, then you have to provide something that's similar out at the edge. Otherwise, its assumptions might be violated. But there's other things. If you really care about disconnected operation, well, it means that the application shouldn't get stuck just because the internet is down for 10 minutes or 10 days, right? Which is something that people might not think about when they're running these applications at the edge. And I think that was about it. Sorry for speaking quickly, but any questions? There's some microphones here.
Just breaking the ice, given that you have an iceberg.
Yes.
So have you come across scenarios where, I think there's one scenario where you have the edge devices and they're reaching out to the controller and you can go in to test the validity of the hardware and the software to the controller.
Mm-hmm.
But in many cases, it's a one-to-many relationship, or I've seen that at least, where you have the device and it's pulling info from on-prem repos and cloud repos. So the internet might be down, you might not reach your controller, but you might still go and reach other repos and sources of information that the device can refer to. How do you handle keys and attestation in that scenario? It's a little bit more distributed than that controller to edge device scenario. Maybe you can expand a little bit on that.
Yeah, I mean, some of it is sort of in this picture, right? And there's actually more to this, right? Yeah. That you know, the sort of attestation is happening this way, right? That's what I talked about. That, okay, before this guy will actually tell it to say, hey, go deploy this application or change this application configuration, it will make sure it's attested, as well as that the actual storage sitting here is actually then encrypted, sort of sealed under that, right? But there's a separate piece which is, well, what about these apps and their security, right? That, you know, they talking to some local, you know, historian, SCADA systems in the factory, whatever, right? How do they actually handle that? Well, in many cases, those things today, I think people are pushing out the credentials for that with things like CloudInit, which is something that people use in the cloud. And it's okay, right, I would say. Because that stuff is now actually ends up in the encrypted application volume. So it's still sort of the same property that if you don't change the hardware here, you still have those credentials around, right? There's another one in terms of, which isn't shown in this picture, which is something that we realized was that, well, you're going to deploy applications here. You're going to have new versions of this EVOS runtime. Where do you pull those things from? Well, it turns out that you can pull them from the cloud. You can pull your containers directly from Docker Hub, right? And you can have S3 buckets pulling them from somewhere. In practice, people actually prefer putting all of that stuff locally, so that you have some data stores you put somewhere inside your enterprise, maybe distributing them. But what you're getting from the controller is just saying, here's the metadata. And that metadata basically has, you know, the SHAs, and then it's actually signed by the communication path here, so that you can say, I can securely go and pull that new version of Ubuntu or my app or whatever from anywhere, because I know the actual, you know, SHA of that thing, so I know that if I'm getting those bits for that SHA, it must be the right thing. So, but in the application domain, it can be a lot more sort of diverse, right? But at least this is, I would say, reasonable, right? But are there other places where people need more flexibility in the applications? Haven't seen that yet.
That makes sense. Thank you.
Other questions? Okay. I think we're at time. Thank you, everybody.